Okay, so we're going to talk a little bit about logarithms as they relate to exponential functions. So say we have a problem like this. There's a power function. If we want to solve for this variable, you take the cube root on both sides or raise both sides to the 1/3 power, and we get x equals something or another. Okay. Well, what if we have an equation that looks like this? Algebraically, we don't have any way to solve for this variable, x. We can't take the x root on both sides and come up with a value of x. So what happens is we've got this thing called a logarithm. And what a logarithm is simply an exponent. And what it is, so this becomes a logarithm. Ugh. Let's try that again. Logarithm. M's have two humps. And all that is, a logarithm is just an exponent. Okay? And in this case, that exponent is the exponent that turns 3 into 14. So let's look at a problem that maybe we could solve without using any fancy techniques. So here we've got a problem 2 to the x power equals 8. So we want to know what exponent turns 2 into 8. Well, we can't solve this using algebra, but we can using logarithms. So if we say this is the exponential form of an equation, it has an equivalent logarithmic form. And that is this. So this is logarithmic form. These two statements, these two equations are identical. This says 2 to the x power equals 8. The logarithmic form says, how we read it is log base 2 of 8 equals x. That means, so we said a logarithm is just an exponent, so here's x. It's an exponent, and it's a logarithm. Okay? What this is saying is the exponent that turns 2 into 8 is x. We're thinking of it this way. We've got 2 to the x power equals 8. Okay, so think of some things we know. So 3 to the second power equals 9. 5 to the third power equals 125. 10 to the negative 2 equals 1 over 100. Okay? These are exponential forms. In logarithmic form, this would be log base 3 of 9 equals 2. In logarithmic form, this would be log base 5 of 125 equals 3. And this would be log base 10 of 100th equals negative 2. Okay, so the logarithm is an exponent. There's the exponent. The logarithm is just an exponent. The logarithm is an exponent. 3 to the second power equals 9. 5 to the third power equals 125. 10 to the negative 2 equals 100. So all the logarithm is log base 3 of 9. What exponent turns 3 into 9? Well, 3 raised to this power makes 9. Log base 5 of 125 means what exponent turns 5 into 125? Well, 5 to the third power equals 125. And then here, log base 10 of 100th, what exponent turns 10 into 100th? Well, 10 to the negative 2 is 1 over 100. So again, all the logarithm is an exponent, and it's the exponent that turns one number into another number. So generally, that's what we're dealing with when we're dealing with logarithms. Now, what we'll do and what we can do on our calculator, we've got a couple of specific situations. So log base 10 of 1,000, log base 10 of 1, log base 10 of 1 over 100. Okay. So when we have log base 10, or we're trying to figure out 10 raised to what exponent gives us 1,000, 10 raised to what exponent gives us 1, 10 raised to what exponent gives us 1 over 100. When we have log base 10, this can be simplified as just log. So if we have log 1,000, that we assume that the base, if we don't have a base here, it means base 10. So log 1,000 means what exponent is 10 raised to make 1,000. This would be log 1. This would be log 1 over 100. Now, in your fancy calculators, so on your fancy calculator here, there's this button that says log. So if I type log 1,000, enter, it says 3. That means, going back here, 10 to the third power equals 1,000. Log 1 equals 0. That means 10 raised to the 0 power equals 1, which anything raised to the 0 power. And then log of 1 over 100 equals negative 2, as we saw before. So what the calculator does is lets us find anything with a base of 10. Likewise, if I had something log base e, log base e of 2.7, 1828, 1828, 45945. If it's base e, this is rewritten as ln 1, or the natural log of 1, with e being the natural base. Log base e here, ln of 2.7, 1828, 45945. Okay, so these are two specific cases. If we have base 10, we can use the log button on our calculator. If we have base e, we have ln. So here's this button on the calculator, ln. So ln 1 should equal 0, because e raised to the 0 power equals 1. And then for ln of 2.718281828459.045, that's 1, because e to the first power equals this number, basically e. Okay? So we've got our calculator now that we can use to solve logarithmic problems. So how about we go back to our initial problem and see if we can solve that using our calculator. Well, We don't have log base 2 on our calculator, but using what is known as the change of base formula, we can rewrite this as log 8 over log 2, or ln 8 over ln 2. I won't get into all the fancy algebra, etc. But if I've got log base something of something else, it can be rewritten. So log of this number over log of that number, or ln of this number over ln of that number. So for example, if I had log base 3 of 27, that's log 27 over log 3, or ln 27 over ln 3. Log base 5 of 25, that equals log of 25 over log of 5, or ln 25 over ln 5. So for this one, maybe we can figure out that 2 to the third power equals 8. Here, 3 to the third power equals 27. 5 to the second power equals 25. So what happens when we do these problems on our calculator? So we've got log 8 divided by log 2 equals 3. Ah, perfect. So you're telling me it doesn't matter that whether I use log or ln? Nope, apparently not. Let's go over here. Log base 27 divided by log of 3. That equals 3. ln 27 divided by ln 3. That equals 3. Log 25 divided by log 5 should equal 2. It does. ln 25 divided by ln 5 equals 2. So now we can figure out logarithms for any base using ln or using log. And that'll help us solve exponential problems. So let's take a look at a problem like this. 3 to the x equals 11. No idea. I know it's going to be somewhere between 2 and 3. I know that because between 2, I know x is going to be between 2 and 3 because I don't know how to write a 2 apparently. That's a 2. 3 squared is 9. 3 cubed is 27. So 11 must be somewhere between 3 squared and 3 cubed. So x is going to be between 2 and 3. Well, I can rewrite this in logarithmic form. Again, exponent, which is the logarithm. Log base 3 of 11 means what exponent turns 3 into 11. Using that change of base, I got log 11 over log 3, or ln 11 over ln 3, which gives us log 11 divided by log 3 equals 2.1826, etc. So somewhere between 2 and 3. ln 11 divided by ln 3, same answer. Okay, so we can now solve any problem involving exponentials by changing to logarithmic form. So think of a problem, you've got some exponential equation of this form. So let's say you started with $100 in the bank, and you get annual interest of 5%. How much will you have in 6 years? Well, that's pretty straightforward. How much you'll have is A is your starting point. Your growth factor is 1 plus the growth rates, or 6, and let's see, you'll have 100 times 1.05 to the 6th. You'll have $134.01. Okay, that's fine. What if, now I say, you started with $100 at that interest rate, when will you have $250? So what we're looking for, since we want to find when, we're going to be solving for t. So we know what we're going to end up with. We know we started here. We know our growth factor. We just don't know t. Well, how am I going to solve this equation for t? Well, the first thing we'll do is divide both sides by 100. We get 2.5 equals 1.05. So don't know how to solve this algebraically, so we can use logarithms. So we can change this using from exponential into a logarithmic. So we can say log 1.05 of 2.5 equals t. Okay? And then using our change of base, you can say, well, that's log 2.5 over log 1.05, or ln 2.5 over ln 1.05 will give us t. And using our calculator, log 2.5 divided by log 1.05 is 18.78. So almost 19 years for it to become $250. But let's just use that. And can we check our answer? Sure. Let's check it this way. What is, if we start at 100, 1.05 to the 18.78, what do we get? Well, 100 times 1.05 to the 18.78, that equals pretty darn close to 250. Okay, we've rounded a little bit, but that's how we can get our answer there. So the change of base is a nice way to do things. Another thing you can do to solve this problem is taking logarithms on both sides. So you can take logarithm on this side, logarithm on this side. Or likewise, you can take natural log on both sides. So just like we can add and subtract the same thing on both sides, we can multiply and divide by the same thing on both sides, we can square both sides, we can take square roots on both sides. We can also take logarithms on both sides. So if And thinking about it, if this thing equals this thing, well, then the log of this thing should equal the log of that thing. Okay? So let's do it with log. So if I've got log 2.5, on the right side what happens, if we have an exponent within the value that we're finding the log of, the exponent comes outside. So for example, here's an example. If I've got log of 10 cubed, that should equal 3 times the log of 10. Well, excuse me, 10 to the third power equals 10 to the third, so I'd raise 10 to the third power to get 10 to the third. Is that the same as 3 times log base 10? Well, 10 to the first power gives you 10. So we can always, if there's ever an exponent inside, we can take that exponent out and put it in front. So at this point, we've got log 2.5 equals t times log 1.05. Now what we can do is divide by log 1.05 on both sides, and we got log 2.5 over log 1.05 equals t, which is what we found before, which is roughly 18.78. Now this is also going to work if you're dealing with things involving continuous growth. So what if I started with $100 and got 5% continuous interest of 5%? Remember, we've got Q equals PERT, and we've got continuous compounding. So P is the original principal, or the starting point of 100. 5% is the continuous growth rate. So when will my initial $100 become $250 if I'm compounding continuously? Compounding continuously. So continuously is where we bring in e to the equation. So I'm going to end up with 250. I started with 100. I'm continuously compounding at 5%. What's t? How many years is that going to take? So again, we'll start out. Let's divide by 100 on both sides. And we get this. Again, we've got the variable as an exponent. We don't know how to solve that algebraically, but we can use our knowledge of logarithms to solve this. So what we can do is we could take the natural log on both sides, or ln on both sides, and see what we got. Well, here's what happens. First of all, we said if we've got an exponent within the thing we're finding the logarithm of, it can come outside. So ln of e to the 0.05t equals 0.05t times ln e. Okay, so this exponent comes outside, or out in front, and ln e. So what is ln e? Well, that's what exponent do I raise e to? So ln is log base e. What's log base e of e? What power do I raise e to get e? Well, that's just 1. So ln of e to the 0.05t becomes 0.05t times 1, or just 0.05t. Well, what does this tell us? Well, that tells us here, if ever I take ln of e to some power, the solution, or the answer, is just that exponent. So this equation here, ln 2.5 equals ln of e to the 0.05t, simply becomes ln 2.5 equals 0.05t. Divide both sides by 0.05. You've got ln of 2.5 over 0.05 equals t. And using your fancy calculator, ln 2.5, ln 2.5 divided by 0.05 equals about 18.33. So roughly 18.33. Meaning, in about 18.33 years, your $100 will turn into $250. And we could check this. 100 times e to the 0.05 times 18.33. 100 times second function e to the 0.05 times 18.33 equals just over 250. We rounded it a little bit, so it's not going to be exactly 250, but it's basically 250. Okay? So that's how we can solve equations both using logarithms, ln or log.